So the last thing we didn't quite get to in 1.3 was what's called a piecewise function. And it's when your graph is drawn with two functions or more instead of just one. And the idea is you've got two different formulas that you're going to use when you draw it. You use one of the formulas sometimes, and you use the other formula the rest of the time. So let's say we had like a formula that calculated the price to buy tickets. You might use one formula if the age of the person buying the ticket is under 18, and you might use a different formula if the age of the person buying the ticket is over 18. So we have two different formulas, and 18 is the kind of the cutoff. Under 18, use the first formula. Over 18, use the second one. So it's two formulas instead of one. So what you're doing is, in my case, I broke the domain up into younger than 18, older than 18. It doesn't have to be the number 18. And I could break it up into more than just two parts. I could say, younger than 5, between 5 and 18, and then older than 18. So maybe there's a price for really young kids, older kids, adults. But you can split it up into as many pieces as you want. And we use a different formula for each part. So basically what I'm going to show you is how you graph a piecewise function on the calculator. We're going to graph a piecewise function that has two parts. We always will do two. Okay, so that's what a piecewise function looks like. They usually put this bracket, and then they give you two formulas, and then they give you the condition when to use the formula. So you're going to use the top formula if you want to figure out a value that's less than 1. You're going to use the bottom formula if you want to figure out a value greater than or equal to 1. So let's say I wanted to figure out what I get when I plug in 2. If I plug in 2 for x, and I say, give me the answer, would you plug 2 into the top formula or the bottom one? Which one? Bottom, yeah, because 2 meets this condition. So when you plug in 2 for x, you get 2 cubed is 8, minus 4 times 2 is 8. You get 0. Now what if I wanted to plug in, let's say, -1? Which formula would I plug into, top or bottom? Top, because the top formula is to be used under the condition less than 1. And -1 is less than 1. What if I had exactly 1? Top or bottom? Bottom. Yep. So all I'm going to show you is how you type that in on the calculator. Now the calculator does a pretty good job of graphing it, but it's not perfect. We have to tweak it a little bit. So the key to type this in is you have to use parentheses. That's what's different. So we're going to put parentheses, 3 minus x squared. And then next to it in parentheses, we're going to put the condition x less than 1. So that condition also has to be in parentheses. Now I haven't shown you where the less than sign is. So I'm going to show you how you can find that right now. To get the less than sign, you press second, math. When you press second, math, you'll get a list of the inequalities. We want the less than sign and 1. Right, and we're going to do that again. I'm going to type in my other function, x cubed. Make sure you hit the right arrow to get out of the exponent. Minus 4x. And then next to it, put the condition in parentheses, x, second, math, and greater than or equal to is option 4. So if this was perfect, when you graph it, the blue graph wouldn't show anything above the number 1. It would just stop, and there wouldn't be anything else. The red graph wouldn't show anything below the number 1. Okay, but I'll show you what happens. So here's the blue one. That's good, that's good, that's good, that's not good. It shouldn't show that part. It shouldn't show that part. It should show that part. Okay, so what this should really look like, let's just take this, is it really shouldn't be drawing on the axis. It's like once it gets to 1 on the blue one, it should just be done. But it doesn't know what to do, so it just draws that line right there. Okay, but if I trace over it in black, that's what this should really look like. So it's a graph of 2 different things. The first part is the 3 minus x squared, and the second part is the x cubed minus 4x. Now, one other thing we have to do. The blue one, okay, the 3 minus x squared. When you get to 1 in the blue one, do you include 1 or not include it?
You include it. You don't.
You don't include it.
On the first one.
And what's the symbol for not including something, like when you're doing a number line? Is that the open or the closed circle? Open. So when you get to 1, you don't include it. How about in the bottom one? When you get to 1, do you include that?
Yes.
Yes. So what this graph should look like, completely properly drawn, is just like that. And that's the part we need to get to yesterday. That's it. Any questions on that? Yes?
How do you do the inequalities again?
Second and then math. Okay. Anything else on that? So the calculator can do most of the work for you. It just, this horizontal line thing shouldn't really be there. And you can't put the little circles on the end to tell you if it should include or not include the very end of the graph. All right. So what we're going to focus on for the rest of today, the real lesson, is 1.5. And that's on quadratic transformations and how we can transform them. Transform means to move it or stretch it. Moving means left, right, or up and down. And stretching, we're just going to focus on stretching something vertically today. You can stretch horizontal, but we don't in this section. So in general, a quadratic function looks like that. It's ax squared plus bx plus c. And those a's, b's, and c's can be any number that you want, except a can't be 0. Let me write that down. So a, b, and c can be any real number. Positive, negative, fraction, or decimal. But a can't be 0. The reason a can't be 0 is because if you filled in a 0 right here, what's 0 times x squared? 0. Now all you have is bx plus c. That's not a quadratic anymore. That's like mx plus b. And that's what shape?
Straight.
That's just a straight line, right? That's just mx plus b. So we don't want a to be 0, because then that messes it up from being a quadratic. But that's what quadratics look like. Okay, I'm going to graph y equals x squared. I just want to see if we remember what that looks like. Does anyone remember what the shape there is called?
Parabola.
Yep, that's a parabola. And now what I'm going to do is I'm going to replace the x with a negative x inside parentheses, just like this. Negative x squared. Now I'm going to hit graph, and I want you to watch how this graph compares to the first one. How does it compare to the first one? Yes, it looks the same, but something actually did happen. Does anybody know what the negative did, but you can't really tell on this one because the y-axis is a line of symmetry? Yep.
It flipped.
Yes, the parabola got flipped over the y-axis. But because a parabola is symmetrical, you can't tell when you flip it. Okay, but that's basically what the negative does. When you put a negative on the inside, it causes the parabola to flip over the y-axis. And if you can graph this and that, and they look identical, like we just did, that means your picture has a line of symmetry on the y-axis. When you draw a parabola, it could be the lowest point or the highest point. Begins with a V. Does anybody know what that's called? Yep. Vertex. Yep, the vertex. So the low point is the vertex, and again, it can be the highest point if you flip. So the first transformation we're going to look at is what happens when you graph something like x squared compared to 3x squared. What happens when you put a number in front of x squared? So we'll type a couple in on the calculator and kind of see what that looks like. Okay, let's graph all three of these. So we've got x squared. This is how you can do 1/3. That's one way to do it. 1/3 x squared. And 2x squared. Okay, and let's look at all three. Okay, so there's the original. Here's the 1/3 in red. And then here's the 2x in black. Okay, so what happened there? What did those different numbers do to the parabola? Yeah.
The function made it wider.
Yeah, so it makes it like wider or narrower. And if you think about, like here's parabola. If I take that parabola and I stretch it vertically, okay, like this. When you stretch something vertically, it makes it narrower and it makes it longer, taller. If I take the same graph and I compress it vertically, okay, compress it, come on, there we go. When you compress something vertically, it starts to look wider. Just think like if you had like Play-Doh, right? And you compress it, what's going to happen? It's going to start to spread out. So if you compress it, it squishes out and gets wider. Okay, these are called vertical stretches. A stretch makes it taller and skinnier. A compression makes it shorter and it gets wider. Now, depending on the number you put in front, you're either going to get a stretch or a compression. If you put a number in front that's greater than 1, that causes the graph to stretch. The bigger the number you put in front, the bigger the stretch you get. More and more and more skinny. Now, if you put in a number between 0 and 1, like 1/3, or 0.5, 0.2, anything between 0 and 1, that's going to cause the graph, I'm going to put a better word there, I'm just going to say compress. So we describe this by either saying the graph stretched vertically or compressed vertically. That's what happens when you change the number in front of x squared. Any question on that? Okay. All right, so now let's do two things. Let's not only put a number in front, but let's put a negative with it. These two things are separate. Same thing here. The 2, that's going to cause it to stretch, but the negative is going to cause it to do something else. Now, you may have a guess what the negative is going to do based on something I already showed you. Does anyone have a guess what happens when you put the negative here? It's in front. It's not like we put it inside in parentheses. I just showed you that. It's a little different without parentheses, but it's still the same kind of idea. Yeah?
Over the x-axis?
Right. When you put a negative in front, that causes it to flip over the x-axis. Okay, so I'm just going to do x squared, and then I'm going to do negative x squared. I'm just doing the first one. There's the original. And now the new one is opening down, and it's been reflected over the x-axis. So you can say, like it's a vertical reflection, or you could say reflected over the x-axis. Same idea. Okay. Important thing to remember is negatives cause reflections. Horizontal reflection, vertical reflection. The big difference is whether the negative is inside the parentheses or whether it's outside in front of the whole thing. And that's going to be kind of the theme of every transformation we do. If you do something on the inside, it's always horizontal. Some type of horizontal reflection, horizontal shift, horizontal stretch. If you do something outside the parentheses, like out in front, it's going to be vertical. Vertical stretch, vertical shift, vertical reflection. Okay, but just remember, the number here and the negative here are really two things happening, not just one. Okay, so what they want to know in this one is basically, how could you take the graph of y equals x squared and change it into negative 5x squared? Well, first thing to figure out is how many transformations would it take to change this into that? Yeah?
It's either 1 or 2.
1 or 2? Anyone have a thought whether they confidently think it's 1 or 2? Isaiah?
2.
Yeah, it is going to be 2. Now, the order you write them in is important. I'm going to tell you that order later on. For now, I'll just give you what the first one is. The first one has to do with the 5. Okay. What is the 5 going to do? Yeah?
Vertical stretch by factor of 5.
Exactly. So you have to say vertical stretch by, and then you say factor of 5. So that's what the 5 does. Now you have to write down what the negative does, and that's the last step. Alex?
Over the x-axis.
Yep. So reflect. Again, you can say, he said over the x-axis. That's fine. You can also say vertically, because reflecting over the x-axis means if you had a picture like this, it would look like that. It's a vertical reflection. So reflect over x-axis. And that's it. That's how you describe the transformations. Questions on that? Okay. Let's see what these do. So this type of transformation is not multiplying. There's not a negative in front of the x squared. It's adding or subtracting a number on the end of the function. So I'm going to graph it, but before I hit graph, does anybody have a guess what the graph of x squared plus 2 is going to look like? What do you think the plus 2 is going to do? Yeah.
Does the 2 represent where the line will cross through the y-axis, like the y-intercept?
So the 2 is going to be the y-intercept in this case. And how about the transformation itself? Yeah.
A vertical shift up by a factor of 2.
Yeah, you could just say up to. You only have to say factor when you do stretching. So in this case, we could just say shift up to. You could say shift up 2 units. But when you do a plus 2, eventually you'll see it. There you go. So it's a shift up 2. Right, let's write it down. So y equals x squared plus 2 is a shift up 2 of y equals x squared. Now the next one, y equals x squared minus 3. Without graphing it, what do you think is going to happen there? Yep.
So it's shift down 3?
Yeah, x squared minus 3 is a shift down 3 of y equals x squared. That's it. Yeah. Now, when we shift it up or down, you're literally just taking and moving it somewhere else. You're not stretching it. So this type of transformation is called a rigid motion transformation. It doesn't distort how the picture looks at all. It just takes it and moves it somewhere else. So the idea you want to remember is that when you have x squared plus k, if k is greater than 0, it shifts it up. If k is less than 0, it shifts it down. Now, why did I do that? Shift down, absolute value of k units. Why didn't I just write shift down k units? How's that? Okay. Yeah?
Because you can't move a negative number, you still have to move a certain distance a positive way.
Right. So if k is negative 3, we don't want to write shift down negative 3 units. If you say shift down negative 3, I guess it's like you're really saying shift up, because it's like a double negative. So don't do that. You can shift up 3, you can shift down 3. That's it. So is there any question when a graph would shift up and when it would shift down based on k? All right, have a good afternoon.
You too.
Right, so we've done adding and subtracting on the end of the function. That's outside the parentheses. What do you think is going to happen if we add or subtract inside parentheses? Yeah.
It's going to be a horizontal shift, left to right.
Right, it's going to either shift left or right. The important thing is which way is which. So let's do x squared. And now let's do x minus 3 squared. Which way do you think x minus 3 is going to go? Think it's going to shift 3 units right or 3 units left? Yep, go ahead.
It's going to shift right 3.
Okay, so you think it's going to shift right 3. Does anybody think left 3? Left 3? All right, so, it is negative -3, so you'd think it would go to the left. Well, let's graph it. Here's the original, with the vertex at the origin. And here's the -3. It does go to the right 3 units. Okay, so -3 will shift right 3. So y equals x minus 3 squared is a shift right 3 of y equals x squared. All right, well, if x minus 3 is going to shift it to the right, what do you think x plus 2 is going to do? Yeah, positive goes left. This is like the opposite of what you would think. So somehow we've got to remember that this is the opposite. The vertical wasn't. Positive was up, negative was down. That made sense. This is like backwards. So this is a shift left 2 units of the original. So this is a horizontal shift, and again, it is a rigid motion transformation. There is no stretching that's happening. It's just sliding. Now we got to remember which way is which. So if you have a graph that you've added a number inside, if the value is greater than 0, so like x plus 2, x plus 5, something greater than 0, which way does a plus shift the graph? Yeah.
To the left.
To the left. Yep. So you're going to shift left k units. Oh, did I use k? I used h. Sorry. Now, if h is less than 0, like -2, -5, which way is the graph going to shift if h is less than 0? To the right. Yep, that's going to shift to the right. And same deal. We don't want to say like shift right -5 units or shift left -5. We just say shift left 5 units, shift right 5 units. You never shift by a negative number. Okay, what do we call this point again? At the very bottom of the parabola?
Vertex.
That's the vertex. So now we've talked about shifting left and right. We talked about shifting up and down. So what we can do now is we can write a formula to find the vertex if we shift our graph. And the formula to find the vertex is -h, k. Why is it -h? Negative in this case really just means the opposite of h. And that's because when you shift left and right, it's backwards. So when we find the vertex, this part of it is backwards as well. So take the opposite of your h value, and then just take your k value the way it is. This is left and right. That's up and down. Now, if you draw a parabola, put a line of symmetry. If you shift up or you shift down, what does that do to the line of symmetry? What's that?
Nothing.
Nothing. When you shift up and down, nothing happens to the line of symmetry. So the only thing that affects the line of symmetry is when you shift left or you shift right. So this is what we're going to focus on when we talk about the line of symmetry. Now, the line of symmetry, which way does it go again? Is it horizontal or vertical?
Vertical.
It's vertical. And do you remember when you write the equation of a vertical line, it starts out with a certain letter equals. It's not like the y equals mx plus b. It's a special case. Yeah?
Is that x equals?
Yes, it's x equals. So it's x equals, and then it's whatever number you put right there. X equals the opposite of h. So here's your two formulas for finding the vertex and finding the line of symmetry. I'll leave those on the board. And let's try this. Okay, so our equation says y equals x plus 2 squared minus 3. And we want to find the vertex and the line of symmetry. Okay, what's the formula for finding the vertex? Again, let's put that off to the side.
Negative HK.
Negative HK. So what do you think is going to be my first number for the vertex? It's the opposite of h. I meant to put a plus sign right there, so just fix that in your notes. If you didn't have that, I fixed it here. Just fix it there. Yep.
It's going to be, the vertex is going to be -2, -3.
Perfect. -2, opposite of h. And then k, just leave it the way it is. So the vertex is -2, -3. And how about my line of symmetry? You don't think they know that?
X equals -2.
Yep. X equals -2. Perfect. So that's how you find the vertex and the line of symmetry. Yes?
Can line of symmetry also be set as axis of symmetry, a vertical place?
Yeah, that would be okay. Yep. Now, I told you earlier that when you have a lot of transformations, like shift left, up, reflect, stretch, you have to write them in a certain order. So anytime you have multiple transformations, the first transformation you always want to write down is any horizontal shifting. Left or right. If you don't have a horizontal shift, then you skip it. And you go to the vertical stretch. Now, I skipped something on horizontal. I didn't write anything about horizontal stretch. A horizontal stretch would go right here. It'd go right in between 1 and 2. We're not going to talk about horizontal stretches in this section, so you don't really have to write it down right now. We will eventually, but for now, you don't have to worry about it. So the second transformation is any vertical stretching or shrinking. The third thing would be any reflecting, specifically in the x-axis. Again, these are all if necessary. Maybe you have it in the problem, maybe you don't. I put a bracket between 2 and 3 because technically you can switch the order of 2 and 3 and still get the same answer. But there are certain ones, if you flip them, you don't get the same answer. So you probably shouldn't flip them. You should just keep the order that I'm giving you. And the very last thing that we take care of is any vertical shifting. Okay, so we're going to look at a problem that has some of those transformations, and then we'll do one that has all of them. Okay, so I'll keep that up, and let's look at the problem at the same time. So this says, how can the graph of f of x equals 5x squared plus 4 be obtained from the original f of x equals x squared? Okay. First step. How many transformations do you think it's going to take to get from x squared to 5x squared plus 4?
2.
Yep, it's going to take 2. Let's go through our list and see which ones we have. Horizontal shift. Do we have horizontal shift in this problem? No. Horizontal shift would be if you added or subtracted inside parentheses with the x and then squared it. Like that. We don't have that. All right. The next thing, vertical stretch or shrink. That's when you multiply by a number in front of the x squared. Lily Rose, do we have a vertical stretch or shrink in this case? Oh, well, I mean, like yes or no. Do we have a stretch or shrink in this case? Yeah, so we do have it. Now let's look specifically at the 5, and let's decide what the 5 is going to do. What's the 5 going to do? Yep. Stretch by how much?
5.
Yep, and this is where you can say stretch by a factor of 5. So you do have to say vertical, because eventually we will talk about horizontal. Not today. So vertical stretch by factor of 5. Okay. Next thing we're going to look for is a reflection. Is there a reflection in this problem? Sean, what do you think? No. If we were looking for a reflection, we'd be looking for either a negative in front of the x squared, something like that, or a negative inside the x squared. Both of these negatives would cause reflections. One's horizontal, and it's vertical. But we don't have it. Okay, so last thing would be the vertical shift. Well, we must have it because we need to write another transformation. So now we're going to focus on the plus 4. Anyone tell me what the plus 4 is going to do? Yeah.
It's going to be a shift up 4 units.
Yep. It's going to shift up 4 units. Okay. Any question on example 6? Okay, so 7. And I think this is our last one that we're going to do. Oh, is there one more thing I want to mention? Oh yeah, the zeros. The zeros of a function. Okay, maybe I'll mention that quick. Okay, so describe the transformations first. Y equals negative 3 times x minus 1 squared plus 4. How many transformations do you think this one's going to take?
3. Oh, hold on, 4.
Yeah, it's 4. So the negative 1, the 3, the negative, and then the plus 4. So we've got them all. All right. Let's start with the horizontal shift. What number there control is the horizontal shift? Yeah.
The number after the x?
Yep. So that's the minus 1. And can you tell me in this case which way it's going to move and how much?
To the right 1 unit.
So shift right 1. Perfect. Number 2. Vertical stretch or shrink. Which number is going to control the stretch or the shrink in this case? Yep.
3.
Yep, the 3. And can you describe what the 3 is going to do?
Vertical stretch. Factor of 3.
Perfect. Vertical stretch by factor of 3. The third one is the reflection in the x-axis. Well, we already know we have it, but can somebody tell me what tells you that you have a reflection in the x-axis? Yep, hi Gene.
Is it the negative in front of the x minus 1?
Yeah, it's the negative in front of that 3. That's what's causing the reflection over the x-axis. That, if I put it there, would be a reflection over the y-axis. That's the horizontal. Okay, so this is a vertical reflection. So reflect over x-axis. And the last thing, the +4. Alex, which way is that going to shift?
It's going to shift it 4 units up.
So shift up 4. Okay, not every problem is going to have every transformation. Some might have 2, some might have 3, 4. It just depends.
Where would be the horizontal reflection if it was in our little 1, 2, 3, 4 step?
So the horizontal reflection would be in between 1 and 2. You'd do the horizontal shift, then you would do horizontal stretch. Then you would do horizontal reflection, if you wanted to see what they all are. So you basically handle all the horizontal stuff first. Then you handle all the vertical stuff after it. This is a vertical stretch, vertical reflection, vertical shift. And I could draw, I won't complicate it, but you could technically switch the order I wrote, the stretch and the reflection for horizontal. But again, you're not going to have to worry about that in this section. But that's where it would be.
I had a quick question. So anything after like that, like the x one, like say a +4, that was on the other one, that's always like the vertical shift, right?
Yeah, anything that's at the end is always the vertical shift.
Okay.
I mean, I guess technically you could see something like this in the book. This is kind of a weird way to write it. But that's the same problem.
Mm-hmm.
They just put the -3. It's still outside the parentheses. I usually like to put it at the end rather than the beginning. But that's the same problem. Okay. Yeah. All right. We're doing that. Which means we're going to skip that. And we're going to skip that. So, yeah, this is the last thing. So the last thing is what we call zeros of a function. Okay, and it's a very, very easy idea. The zero of a function is basically a number that I could plug in for x, and the answer comes out to 0. So does anybody see the number that I could plug in for x right there? And I would get an answer of 0. Yep.
Negative 3.
-3. That is the only number you could plug in for x and get an answer of 0. So value for x such that when you plug it in, you get 0 for y. Okay, here's another one. Y equals x squared plus 6. No, let's do minus 16. X squared minus 16. Does anybody see a number you could plug in for x this time that would give you 0? Yeah? 4. Mm-hmm. And negative 4. So this one is a quadratic. It has 2 roots, 4 and negative 4. Quadratics can either have 0, 1, or 2 zeros. Sometimes I call it a root, sometimes I call it a 0. It means the same thing. A root is a number you plug in and you get 0 as the answer. So how can quadratics have 0, 1, or 2? First of all, what's the shape of a quadratic when you draw it? Yeah, it's a parabola. So if you have a parabola and it does something like that, there are 2 spots where it's equal to 0, okay, where it crosses the x-axis. Where a graph crosses the x-axis is the 0. So you can also find it in a picture rather than doing an equation. So parabolas can have 2 zeros. Parabolas can have 1 0 if they just come down, touch the axis, and go back up. Or parabolas can have no zeros. There is no number you could ever plug in for x here and get a y value of 0 because it's been shifted up. And there's a quick way to tell whether the graph is going to have 1 0, 2 zeros, or no zeros, at least for quadratics. So this applies to quadratics. What you need to do is check that. Does anybody recognize that b squared minus 4ac? It's not the whole thing, but it's something. Yeah?
This is the radical of the quadratic equation.
It's what's under the square root when you do the quadratic equation. And if you want to quickly figure out how many times your graph crosses the x-axis, which means how many roots, how many zeros does your graph have, there's really 3 cases. Either b squared minus 4ac comes out less than 0, equal to 0, or more than 0. If it comes out less than 0, it doesn't cross the x-axis at all, and it means there is no number you could plug in to get 0. There is no 0. Here's an example. X squared plus 2x plus 3. At least I think it's an example. Yeah. What's b in this case?
2.
2. And if you square it, you get 4. Minus 4, what's a?
4.
1. And what's c? 3. 4 times 1 times 3 is 12. What's 4 minus 12?
-9.
Negative 8. So I don't know what the roots are. If I wanted to know the actual roots, I got to do the whole quadratic formula. But if I just want to know, is this graph ever going to cross the x-axis? The answer here is no. There are no zeros to this problem. No real zeros. Okay. Now, if b squared minus 4ac comes out to exactly 0, then that means your graph comes down, touches the axis, goes back up, which means that you would be able to find one root to your problem. You'd be able to find one. And then if b squared minus 4ac comes out bigger than 0, you're going to have a situation where your graph crosses twice, which means you have 2 numbers you could plug in and get 0. So we call that 2 zeros. So it doesn't find them. It just tells you how many there are quickly. And that's the last thing. Is there any question on that? Yeah.
What if it's more than 2 zeros?
You can't have more than 2 in a quadratic. The only way you could have more than 2 is if your U-shape, started to curve and then went back down again. That's a cubic. So if you have a cubic, there isn't really a shortcut to figure it out. You just have to draw it on the calculator and see. Yeah. Okay. Any other questions on that? Okay. So I gotta put up the homework. I gotta just change a couple questions though. Okay, so we're not gonna do. Let's see. 40 and 41. And 60. So I think it's 12 questions.
it's over there.
Sounded like it was almost over.
Yeah.
All right, so that's the homework for tonight. We'll check that tomorrow, and tomorrow is the last day of material for this week.